Just a little bit more to say about nucleophilic substitution then, before you have a bit of a practice drawing and naming a few substances, and then also next lesson we look at the reaction between a haloalkane and ammonia, which is another example of nucleophilic substitution. Now, one thing that we didn't mention previously, and which to be honest I quite often try and avoid up to a point, but we do need to address it really, is why the reaction goes the way it does. So in our first lesson, I very much presented it as a matter of fact, which is correct. It is correct to say what we did, that nucleophiles react with haloalkanes in the way they do. But why does it go like that? So you'll notice that this time I've just used the placeholder Nu to represent nucleophile. The important thing is that, as per the definition, a nucleophile is an electron pair donor. It's going to have to be a lone pair for us, so that there it is. And the two examples that we had last lesson, hydroxide and cyanide, both happen to be negatively charged. So this time I'll put Nu minus. However, just to note that the other nucleophile we'll study is ammonia, and it doesn't have a charge, but it does have a lone pair. So the charge isn't like an essential feature. That's just something that we've seen twice, and so you might believe it was. Now, yeah, as we saw, and as you're hopefully already a little bit familiar with, the mechanism goes that a lone pair on the nucleophile attacks, that's what we say for when we mean forms a bond with, so curly arrow to that carbon. And when I say that carbon, I mean the carbon that's got a group 7 atom bonded to it. So in this 2-bromobutane here, it's carbon 2. That, as we saw again, causes a bond to break, and it's the C to halogen bond which breaks, and the electrons go to the more electronegative atom. Now that's something we're going to talk about more now, which is always the group 7 atom for us. Fine, so that was the pattern. We saw that already, nothing new there then. But here's the question for us to consider first of all. Why is it that it goes there? Why does this nucleophile attack this reactant at all? Why doesn't it go for one of the other carbons, or that hydrogen, or the Br? Why does it go to that carbon? And the answer is because it's attracted there. So when we consider that CBr bond, and that's the bond that's about to break, and it's this carbon with its other 3 bonds that we're less interested in right now, where the nucleophile attaches, that carbon is delta positive, and the Br is the same amount, delta negative. So CF, we're not going to worry too much about. Again, I'll make a comment on that in a moment. CCl, CBr, or perhaps CI. Those are all polarized bonds. I want to say a little bit more about CI, but it's a bit of an extra complication that I don't really have to worry about, but I want to address it. So in each case, those group 7 atoms, we can safely assume, are partially negatively charged. And it follows then, and it's because of the difference in electronegativity, apart from CI, which I'll come to, and so then the carbon is delta plus. So there's a driving force behind this reaction, and part of it is the fact that the nucleophile is attracted to that carbon. The nucleophile is electron rich. In this case, it's negatively charged because we're talking about hydroxide or cyanide, and so it's electrostatically attracted to that delta plus carbon, which is why it ends up there, and then this reaction goes on. The outer shells overlap of the nucleophile and that carbon, and change happens. We haven't got to it yet, I appreciate, but ammonia doesn't have a charge, yet it's still attracted to that carbon. Ammonia is obviously 3 NH bonds, basically, and we appreciate that N is one of the most electronegative elements. So the lone pair on that N there is really strongly attracted to positive things, such as C delta pluses, because that N is delta negatively charged itself. We talked about hydrogen bonding. We appreciate that that is really quite a big partial negative charge. It doesn't matter, but those H's are, well, a third as positive as that N is negative, because all 3 NH bonds polarise towards that central N, as in the electron density ends up all on that one N. But there we go. So that lone pair on the N is pumped up with extra electron density, and a similar thing could be said about the O in hydroxide, and it's a bit more complicated with cyanide, but the lone pair on the C is very available to react. So there's an attraction, is what we're saying, between the nucleophile and the carbon, because that carbon is partially positively charged. Now, I did say something about iodide. I was a bit vague, and I was also a bit quick to brush off CF. Let's deal with CF first. This is something we're going to make notes on in a future lesson anyway. But the CF bond is really short because fluorine is a really small atom. It's only got 2 shells, don't forget it's in period 2. Compare that with a CI bond, which is much longer because iodine atoms are much bigger than F. It's got 4 or 5 shells rather than just 2. So what's going on here? Well, when we talk about the length of a bond, we mean the nucleus to nucleus distance. And the more shells there are, the outer shells are the ones that link up. The bond's longer. Longer bonds are weaker than equivalent looking shorter bonds. Here I'm going to say they're equivalent because they're both single bonds. The CI bond is weaker. CF bond, therefore, is really quite strong. In fact, a CF bond is a stronger covalent bond than a CH bond, and we regard CH bonds as being quite difficult to break. So even though the carbon in CF, if it was a fluoroalkane, is really, really delta plus, and so very, very attractive to a nucleophile, actually that second step there, the one where the CBr, or if it was imagine a CF bond breaks, is really quite difficult energetically because the CF bond is really short and really strong. So that's part of another lesson that we'll look at in the future, rate of reaction, comparing fluoro with iodoalkanes. Now another thing I wanted to say about CI bonds. So they are quite weak, so given a chance they will break readily. The thing is, carbon and iodine both actually have the same electronegativity on the Pauling scale for electronegativity. It's not that there's no permanent dipole. Nonetheless, and not just because it's what your examiner expects to see, we will consider CI bonds to have polarization. It's not actually because of a permanent dipole, they've got the same electronegativity. It's because now if you imagine a CI bond here with an even distribution of electron density around it, when something negative comes along, and the I is very big, and that means that this big electron cloud around the CI, because of the size of the I, is really quite polarizable. So when a negative or an electron-rich species comes along, such as a CN minus or an OH minus or an ammonia, but with its delta negative N, I'm just writing Nu, that's nucleophile, remember, it's just a placeholder, it's not a real formula, minus. When something electron-rich comes along, repulsion happens. This is the same sort of description we use for explaining van der Waals forces, and it induces a dipole in the CI bond. Now, we're only interested in that CI bond, if it was I rather than Br, when we're talking about nucleophilic substitution, which is something that will only happen when a nucleophile comes nearby. Now, you might imagine the chemical reaction happening. Let me draw a structure that actually does have a CI bond in. I'll keep it simple, and I'll draw in skeletal style iodopropane there, sorry, 2-iodopropane. When a nucleophile, I'm going to continue to just use Nu as my nucleophile, and I'll put a negative charge on it. It's hydroxide or cyanide. If I add this liquid here, iodopropane, and I add some sodium hydroxide solution, then all the particles are going to be tumbling around and colliding. And so inevitably, some of these nucleophile particles, ions in this case, are going to collide or come nearby the iodoalkane molecule. And when they come close together, repulsion happens. And then they're not just passing each other by, there's an attraction. Once again, at that point we actually would have a delta plus carbon. And so there's the electrostatic attraction, drawing them together. But it's not just an attraction. This isn't making an ionic lattice or something like that. It's actually going to chemically react, meaning chemical change happens, and that's where we get our mechanism go. So here, the electron pair on the nucleophile would react and form products. Again, OH or CN is what we mean when we write Nu, because Nu is, again, just a placeholder, and iodide's been booted out in that process. So even though there's no difference in electronegativity between C and I, whenever this is relevant, there is still a dipole because of repulsion happening and polarizing that big juicy CI bond electron cloud. So that was just one of the things I wanted to mention. Now, before I set the task, I wanted to give you an opportunity to think about naming some nitriles, because drawing and naming is something that we pick up as you go along. So this is something which is going to come in to the task that I've got for you today. And the best way to learn naming is simply to see loads of examples. So let me show you a couple of examples, then you can, as well as listen carefully to what I'm saying, you can sort of reverse engineer what the rule must be to get that. So nitriles are formed when haloalkanes, such as, well, you can name that one in skeletal style, react with cyanide ions. and we get nitrile. So remember, we don't call it an alkyl cyanide or anything like that, we call it a nitrile. Now hopefully you did have a go at naming that one. 1, 2, 3, 4 carbons when I interpret this skeletal formula. So it's bute, saturated, so it's butan, and it's bromobutane, and it's 1-bromobutane. Fine, that's the sort that we've already had a bit of practice on. Now, by comparison, this molecule has actually got more carbons in its chain because a Br has been removed and a carbon containing group has taken its place. That carbon's always going to be considered in the main chain, which means this is now pent something or other, and we call this pentane nitrile. So again, it's just a case of seeing the examples and remembering them. Notice that it's not pentan nitrile. Like if it was an alcohol, it'd be pentanol, pentan-1-ol or whatever. Here it's pentane nitrile. A couple of assumptions are made there correctly. This carbon, not that we have to number anything this time, always gets the prestige of being carbon 1. Once we've got more functional groups looked at over the next couple of weeks of organic chemistry, we'll start talking more and more about what are called priority functional groups. Basically, there's like a league table of functional groups, and cyanide, or sorry, nitrile, is quite near the top. And the idea is that if a molecule's got a couple of different functional groups, then the one that's higher priority, higher up the league, will get the end of the name. That's the kind of prestige. You get the end of the name, and you often get carbon 1 as your sort of title as well. So there was no numbering here, but let me now show you a couple where you would number. Before that, I'm just going to, sorry, I always forget, there's one more thing I want to say, a couple more things actually. There's the skeletal formula of a different nitrile, and again, skeletal, we're going to try and work backwards here. I'm going to actually write the C's on now to work it out. 1, 2, it's 3 carbons there. Those carbons must have 4 bonds, so there's invisible hydrogens, as is always the case with skeletal. But that's got 3 carbons and it's a nitrile, so we'll call that one propane nitrile. So you can just see how the logic behind the naming works. You basically name the alkane that it's based on, but call it something nitrile. There's clearly no H's on that carbon. The other thing I wanted to say before I give you some more advanced nitriles to name, just to give an idea of how it works, bond angles. You'll get away with all sorts of weird and wonderful bond angles. So I could write propane nitrile as just a structural formula, so bond angles are irrelevant. CH3, CH2, CN, it's all good. But if I am going to try and be as accurate as possible, it's worth bearing in mind that that nitrile carbon there is linear. So yeah, it has got 4 bonds, but it's effectively only got 2 bonds in that one's a triple bond and the other is a double bond. So it's got the triple bond N on one side and it's bonded to, well, more carbon, or at least a H if it was just HCN on the other side. And so that bond angle there, we'd expect that triple and single bond to repel to be as far apart as possible is 180 degrees. Now you just write CN. You could have written it like this. You could draw your structure like that, so like the zigzag. But there, that's the same. That's still propane nitrile, except the bond angle is not quite right. So if we want to be really technically correct, nitrile groups are linear. The carbon that's bonded to the CN carbon itself, and the N, so the sort of CCN chain, dead straight line. However, you don't have to be quite as specific as that for your A-level, but I think you should be because it's correct. Now, the last thing I'm going to do before you get a task is just give you a couple of examples of more complicated looking nitriles. So I'll give you these 2. By all means, pause the video and have a go for yourself, but I'm going to talk you through them straight away. I'm just thinking carefully here. Yeah, that's going to have to do. Now, what we said was that the nitrile always claims the end of the name. There are some exceptions to that. If we had a carboxylic acid in there, we'd have a bit of a problem, but that's not for us to worry about for quite a long time in the course, if ever. So cyanide, or rather the nitrile functional group, gets the end of the name, and we said gets the sort of the prize of being carbon 1. So the CN carbon is always carbon 1. The name of the game is to number it and keep the numbers as low as possible, if you have to think that way. So carbon 2, carbon 3, carbon 4. Now, therefore, that is basically butane nitrile, this one that I'm writing underneath, butane nitrile. But clearly there is that OH to deal with, and we've already got something at the end of the name. So if you have a functional group like a carboxylic acid, a COOH, or here a nitrile, a C triple bond N, which is in your molecule, then it will get the end of the name. So you don't get carboxy, you get carboxylic acid. You don't get cyano very often, you get nitrile, the end of the name. Now, of course, the OH we'd recognise as an alcohol, and typically we'd expect that to be at the end of the name. That would have been butan-2-ol, were it not for the CN. We can't call it butane nitrile 2-ol, because then you've got two functional groups at the end of the name. So the OH is forced into what we call a prefix position. It's less important than a carbon-containing functional group, which we've got one of here. So it gets forced to be the prefix, and so rather than calling it anything ol, we call it 2-hydroxy butane nitrile. And following a similar logic, there's no for prefix here as such. Let's keep the numbers as low as we can for this other molecule. Now I can get more longer chain if I go that way. So carbon 3 is going to go to that way. Either of these methyl groups, either one, they're the same, could be carbon 4. The other one is methyl. So to name that then, we've got, well, butane nitrile again. But this time it's a sort of modified form where you've got methyl groups on carbons 2 and 3. So it's 2,3 dimethyl butane nitrile. So anyway, you've had a couple of examples there. You can hopefully see the logic behind the naming system. So here's the task that I want you to do with the rest of your lesson time. Somewhere, there it is. Now, it might be that you just quickly print screen that or just pause on it for a minute and take note. As I said, I want this handed in by the end of today. It shouldn't take you more than, well, what's left of the hour, so you've got about half an hour left to do this. It's just 4 relatively quick and easy mechanisms compared to what will come later, and I want you to have a go at naming. It's not assessed in the formal sense. Obviously, I want you to see that you're trying. I want to see that you've had a pop at it, and I need to look closely at your mechanisms because it's absolutely critical that these arrows are moving in the right direction. Okay, there's a definite pattern to that. And I need to see that you're getting it right with all the rest of the structure intact and shown. So it's the eye for detail here. Don't be put off by question 3. Yes, it's an alkene. However, as I'm saying, this is just nucleophilic substitution, so treat it like any other and have a good go at questions, well, all the questions, but you know, questions 3 and 4 present a bit of a challenge, at least, just having to draw these structures in the first place. So get on with that now. Send me a copy of your work by the end of today. I'm going to say by 6 PM. Just so I can have a quick look before next lesson and make sure you're not making any silly mistakes. Anyway, so there you go, carry on.